We're going to use Euler's method with a step size of 0.2 to approximate the solution of y prime equals y minus x with an initial condition y of 0 equals 2. We're going to use this method to find an approximate value for y of 1. We're not supposed to round anything until the very end. And the first two rows are done for you as an example. So 0, 2, this came from the initial condition. X is 0, y is 2. So I have put 0 and 2 in the x and the y columns. Now, they told us that the step size is 0.2, that's delta x. So for my delta x, my initial x was 0, my step size of 0.2 would give me 0.2, then 0.4, 0.6, 0.8, and 1. So my x column is all done. And I'm going to start off right here at row 2. So I know that this 2.84, this is my new y, so this has to get moved down here. And now I'm going to do dy dx, which is just y minus x, because that is the differential equation. That's the formula for the derivative. So y minus x, 2.84 minus 0.4 is 2.44. And then delta y is dy dx, 2.44 times change in x, which is 0.2. So now I'm going to grab my calculator. 2.44 times 0.2 is 0.488. And my new y is going to be my old y of 2.84 plus my change in y, which is 0.488. 3.328. And that's going to get moved down to the next row. 3.328. Okay, dy dx is y minus x. So 3.328 minus 0.6, that's the x value in this row. And so I get 2.728. And then the change in y is the slope, which I just calculated, times delta x, which is 0.2. So 0.5456. And my new y is my old y plus my change in y. So my old y was 3.328. Change in y is 0.5456. So plus 3.328. You'll notice I'm not rounding anything. I'm carrying all my decimals here. And I get 3.8736. And that gets moved down to the next row. My dy dx is just y, this number, minus x, this number. So I get 3.0736. Delta y is dy dx times delta x. So take the 3.0736 and multiply by 0.2. And we get 0.61472. And that's my change in y, so I add that to my old y to get my new y. So my old y was 3.8736. 4.48832. And that is my new y, 4.48832. So that is my estimate for y of 1. When x is 1, y is approximately 4.48832. So we don't have the tools to solve the differential equation y prime equals y minus x with an initial condition y of 0 equals 2 at this stage. That's why approximation techniques like Euler's method are so useful. You'll have to wait until Math 204, differential equations class, to see how to come up with an exact solution. But that said, I'm just going to tell you this is the solution. That is the function y that satisfies the differential equation and the initial condition. So let's just verify. Y equals x plus 1 plus e to the x. First, let's check if y of 0 equals 2. If I plug a 0 in, I get 0 plus 1 plus e to the 0. That equals 0 plus 1 plus 1, which is 2. Check. The initial condition is satisfied. Y of 0 equals 2. To check the differential equation, I have to make sure y prime equals y minus x. So y prime, that's the derivative of y, the derivative of this formula that you were given. So the derivative of x is 1. The derivative of 1 is 0. The derivative of e to the x is e to the x. Does that equal y, which is x plus 1 plus e to the x? That's y, minus x. So just to be really clear, this is y prime, this is y, and then this is the minus x. Just substituting in for y prime and for y. And I want to make sure this is equal. So the left-hand side is 1 plus e to the x. And the right-hand side, the x's cancel. These two go away. And I get 1 plus e to the x. So these are equal. So we have a solution to the differential equation. Y equals x plus 1 plus e to the x. Okay, so I want to use this to judge the accuracy of my approximation from the previous problem. So in the previous problem, we were using this differential equation with this initial condition, and we're estimating that y of 1 is approximately 4.48832. So Euler's method suggests that y of 1 is approximately 4.48832. But now I have a formula for y, so I can be more accurate. Y of 1 is 1 plus 1 plus e to the 1. 1 plus 1 plus e to the 1 is 4.71828, approximately. 4.71828. So these two numbers are approximately equal to each other. So y of 1 is 4.71828. Euler's method approximated 4.48832. So they're off by somewhere between 2 and 3/10. Point 2 to 0.3 error. Okay, next problem. We're going to sketch the slope field at these 12 points. So slope field for the differential equation y prime equals x squared plus y squared minus 1. So 1 has been done for us at the point 0, 1. We plug 0 in for x and 1 in for y, and we get a slope of 0. So at 0, 1, we would draw a flat tangent line. Okay, so my 12 points are 0, 1, 0, 0, 0, negative 1, and that's all my zeros for x. And then I have 1, 1, 1, 0, 1, negative 1, 2, 1, 2, 0, 2, negative 1, 3, 1, 3, 0, 3, negative 1. And then I'm going to plug all these into the differential equation to get some slopes. So 0, 0, I get 0 squared plus 0 squared minus 1 is negative 1. 0, negative 1. 0 squared plus negative 1 squared minus 1 is 0. 1 squared plus 1 squared minus 1 is 1. 1 squared plus 0 squared minus 1 is 0. 1 squared plus negative 1 squared minus 1 is 1. 2 squared plus 1 squared minus 1. So that's 4 plus 1 is 5. Minus 1 is 4. 2 squared plus 0 squared minus 1 is 3. 2 squared plus negative 1 squared minus 1, so that's 4, plus 1 minus 1 is 4. 2 squared plus 1 squared minus 1 is 4 again. Oh, I did a 2 and I should have done a 3 there. On to the 3's. Okay. 3 squared plus 1 squared minus 1, that's 9, plus 1 minus 1, so 9. And then 3 squared plus 0 squared minus 1 is 8. And 3 squared plus negative 1 squared minus 1 is 9. So now I'm going to plot all of these slopes, roughly. So at 0, 0, the slope is negative 1. 0, negative 1, the slope is 0. And then 1, 1, my slope is 1. 1, 0, slope is 0. 1, negative 1, slope is 1. 2, 1, my slope is 4, steeper. 2, 0, the slope is 3, slightly less steep than the last one. 2, negative 1, the slope is 4. And moving on to the 3's. 3, 1, the slope is 9, very steep. 3, 0, the slope is 8. It's going to be hard to tell the difference here. And 3, negative 1, the slope is 9 again. Okay, so now I have some nicer slope fields where I plotted hundreds of slopes instead of just 12. And instead of just plotting them at the integers, they're at lots and lots of points in between the integers, which gives us a pretty good picture of the solutions. So I want to sketch the solution that passes through the indicated point. So this is my initial condition. I'm just going to trace the slope field, just sort of like that. Trace it backwards too. And then in this one, here's my initial condition, and I'm just going to follow the slopes. Something like that. Since an equilibrium solution is defined as a constant function or an unchanging function, its derivative has to be 0. The derivative of a constant is 0. So that means that a quick way to find equilibrium solutions is to replace the derivative term in a differential equation with a 0 and then solve. So I'm going to replace this dq dt with a 0, 10 minus 1/20th q. So I get 1/20th q equals 10, which means that q is 200. And that is exactly what we came up with when we built the slope field in the demo. So remember, equilibrium solutions can be classified. The one from the demo was called a sink because all nearby solutions were drawn to it. Two other types of equilibrium solutions are sources and nodes, and those are both called unstable. A sink is called stable. So in a slope field shown below, we want to sketch the equilibrium solutions. So find the places where the slopes are horizontal. Slopes are 0, the tangent lines are horizontal. Write an equation for each equilibrium solution and classify it as a sink, a source, or a node. Okay, so I have equilibrium solutions, it looks like here. All my tangent lines are horizontal, and that is the equation y equals 3. Here, that is the equation y equals 1. And, oh, I missed one here. That is the equation y equals 2. And so I've done the first two parts. Now I need to classify a sink, source, or node. So I would do that by looking at, do my solution curves approach or go away from the equilibrium solutions? So if I put an initial condition above the y equals 3, it looks like the solutions all head away. And if I put one below, they come down like this. And then let's see, if I come down here, these ones go up like that. And if I put one down here, they head towards that. Okay, so the y equals 3, solutions to either side of y equals 3 head away. So this is a source. This solution heads away from y equals 3, and so does this one, heads away. At y equals 2, when you look above and below, you see that they both approach the equilibrium. They both are drawn to the equilibrium solution, so this is a sink. And y equals 1, one side approaches the equilibrium solution, but the other side heads away from it, so we call this a node.